last day. Okay, so since the vote yesterday on what I should talk on was an exact tie, I get to make a unilateral decision on who wins the election, which, as Eva pointed out to me, is a fine tradition in this country. So I'm going to talk on Calabi-Yau manifolds. And there's two reasons for this. The first is that there's an elegant and extremely useful construction of Witten on how you get Calabi-Yau manifolds out of gauge theory. And I don't think Johannes Valcher covered this in much detail, and it takes about half a lecture. And it's called the gauge linear sigma model. So the main reason was that I can teach you all with this very important technique in understanding Calabi-Yaus. And then the second reason is that for the second half of the lecture, there's some very nice new results that I can tell you about on a rather new way to get Calabi-Yaus out of gauge theories that hasn't really been explored very much. So I think there's a lot of interesting and new things to do that I can tell you. Firstly, let me tell you, for those who voted in the other camp, what I'm not going to tell you about. So just in 60 seconds, the topic of the lecture I'm not going to give is the following. You take an n=1 gauge theory in 4 dimensions, with NF equals NC, number of flavors equals number of colors. You look at vortex strings in this object. The world sheet of the vortex string has 0,2 supersymmetry. And by studying the quantum dynamics of this 0,2 vortex string, you can rederive Seiberg's formula for the quantum modified moduli space up in 4 dimensions. And it turns out the relevant physics on the vortex string is world sheet supersymmetry breaking. So if anybody's interested in this, I'd be happy to tell you in the break or break it. Okay, so the title of this lecture is Non-Abelian 2D gauge theories and Calabi-Yau. And I've given you the PowerPoint slides for a related lecture. It's the second half of those slides I've given you that I'll talk about here. So the basic idea is due to Witten in a paper called Phases of n=2 Theories in early 1992. This is a totally beautiful paper. I recommend all of you to read it in some detail. And the idea is really very simple. You're interested in studying conformal field theories with a target space that's a Calabi-Yau manifold. You might be interested for many reasons. Maybe this is your favorite string compactification. Maybe you're interested in more formal things, mirror symmetry, something like this. But basically, you want to get some handle on how to understand that conformal field theory. So Witten said that you shouldn't really think about writing down the sigma model with the particular Ricci-flat metric that maybe gets corrected at 40, all of this. What you should do instead is write down a gauge theory. This is a gauge theory in 2 dimensions. And you construct the gauge theory such that under renormalization group flow, it flows to your Calabi-Yau sigma model CFT. And the basic idea is that the target space of this conformal field theory, the sigma model, which is the Calabi-Yau manifold, is constructed from the vacuum moduli space of the gauge theory. So target space of the sigma model is equal to the vacuum moduli space of the gauge theory. Okay, so there's a few little hard things that you have to do here. Given your favorite Calabi-Yau manifold, you've got to figure out what gauge theory you should write down that flows in the infrared to this particular Calabi-Yau manifold. So what I'm going to do in this lecture is explain to you how you start constructing these things. The advantage of this is that 2-dimensional gauge theories, like 4-dimensional gauge theories, are asymptotically free. So if you work in the ultraviolet, everything is weakly coupled. You can start to calculate very easily up here. And there's certain quantities which are protected under RG flow. That is, they don't change as you flow down to the infrared. So you can calculate things up here which you're really interested in down here, and you can get away with it. That's really the beauty of this model. You know, I'm reminded there's a quote by Schwinger, a really bitter quote actually. I think toward the end of his life in the 1980s, he says, the trouble with those Feynman diagrams is they brought computation to the masses. Okay? They allowed people other than Schwinger to work on quantum field theory. This is called a gauge linear sigma model. And the beauty of this gauge linear sigma model is it brings geometry to the masses. Okay? It allows bozos like me to prove theorems that mathematicians are interested in, even though my algebraic geometry really isn't that hot, but I can compute Feynman diagrams. Okay, so let me show you in 3 steps how you construct a Calabi-Yau manifold out of a gauge. So how to construct Calabi-Yau. So step 1, well, let me just introduce the kind of theories we're interested in. We're in 2 dimensions because we're interested in 2-dimensional conformal field theories with n equals 2, 2 supersymmetry. So this is exactly the kind of theories I've been discussing in the context of vortices for the last 2 lectures. And step 1 is to consider the following theory, which should be familiar. You take a U1 gauge theory in 2 dimensions plus n chiral multiplets of charge plus 1. And then you write down the potential dictated by n equals 2 supersymmetry for this theory. Okay? So what does the potential consist of? Well, essentially it's the d term that's important. So the potential is e squared over 2. E squared is the gauge coupling constant. Some of your chiral multiplets, should have given those a name. And then you put a phi Heliopolis parameter in there, and you take r to be much greater than 0. And then there's also another term which couples the vector multiplet scalar to these guys. So this is precisely the potential I wrote down before. Before I wrote it with a Lagrange multiplier here, and those squared, the Lagrange multiplier was d. So to get this form, I just integrated out that d term. Then, of course, I should divide out by U1 gauge actions, and the U1 gauge action, because all these things have charge plus 1, is simply to rotate the phase of all the phis. Okay, so this is something that we've really looked at in detail in the last 2 lectures. As you know, it doesn't define a Calabi-Yau manifold, it defines the target space CPN. So this is the gauge linear sigma model for CP n minus 1. Okay, so let me draw a picture of CPN just here. So this is CPN. Again, just to remind you, CPN is defined by these 2 relationships. The fact that this is equal to 0, so the sum of the phi I squared is equal to r. R is the size of CPN, and you divide out by this gauge action. Okay, but as I said, this isn't a Calabi-Yau manifold, and one way you see it's not a Calabi-Yau manifold is that the theory isn't conformal. If you look at the size of CPN given by r, and as we saw yesterday, this is something which runs. There's a 1-loop beta function, and as you flow to the infrared, the size of the CPN begins to shrink. This is not CFT. And this is reflected by the running of the phi Heliopolis parameter. Which flows in the following way. Okay, so step 2. Well, the next step is to try and head more towards a conformal field theory. So we've got a theory where the coupling constant runs. We have similar theories in 4 dimensions, QCD as an example. Well, we have QCD. We know there's ways to get conformal theories in 4 dimensions by adding more matter content until we get to a stage where we cancel the beta function completely. N equals 4 supersymmetry is the typical example. So we could try and do exactly the same in 2 dimensions. We could try and add more matter to the theory so that we manage to cancel the 1-loop running of Phi-Leopolis parameter, and try and keep this to be a marginal parameter, and hope that gets us closer to a conforming field. So step 2 is to add more matter, or more charged fields. Well, how are we going to do this? The one-loop beta function that we have here is proportional to n. That n comes about because it's plus 1 n times. Okay? So the one-loop beta function, which is the coefficient of this term, is proportional to the sum of the charges of all the fields. And you can see this very simply from a Feynman diagram. The Feynman diagram that contributes is a tadpole for D with the charge field phi I running in the loop. It's just the bosons that run. And of course, this is proportional to 1 power of the charge, not the charge squared. Essentially, what you get a tadpole for D. Remember, the Phi-Leopolis parameter here came in originally from an okay, so D is the usual D term in a supersymmetry multiplier. This is how it looks. When you integrate out D, you get this D term potential. So it's you put a tadpole for D, which comes from this interaction, which you then absorb into a renormalization of R. So that's how that works. Okay, so if we want to get R to cancel, or R not to run, what we need is to add enough fields so that the sum of all the charges is equal to 0. So we've already thrown in n objects with charge plus 1. So there's various ways we can cancel that. We could throw in another n objects with charge minus 1. But it turns out the interesting thing to do is to throw in just one object with charge minus n. Okay? So we'll choose n phi I with charge plus 1 and one object p with charge minus 1. Okay, the D term becomes this. The vacuum moduli space of the theory, well, if R is greater than 0, we've got to turn on the phi i's and the p's. So the vacuum moduli space is defined by this being equal to 0 modulo the gauge transformation. And the gauge transformation is all the phi i's transformed with charge plus 1 and p transforms with charge minus. Okay? So this gauge theory, notice that because R is non-zero, the phi i's have to turn on to make this 0. And as soon as the phi i's turn on, you can never turn on this guy, sigma. So sigma just never plays a role in this whole construction much later. So for now, we're just interested in this term being 0. And so you have a bunch of phi i's, a bunch of p's satisfying this algebraic relationship where you identify configurations related by this gauge. Okay, so this does define a Calabi-Yau manifold. We've got a Higgs branch of the theory now, given by this. Phi-Leopolis parameter no longer runs because this running here is cancelled by the P field that we've introduced. However, it's not really what we want because this Calabi-Yau manifold is non-compact. And it's very easy to see this from here. You see, before you had the P, you had a compact manifold because it was the mod phi I squared is equals R, which is a sphere. It's nice and compact. But now we've got the P, and in particular it comes with this minus sign. This minus sign is because it had charge minus n. And this means that I can always make phi as large as I like at the expense of making P as large as I like. Okay, so there's no bound to how big this manifold is. So in fact, this manifold defined by this is a Calabi-Yau, which is in fact the ON-1 line bundle over CPM. So you can think of this in the following way. Here's CPM, and at every point on CPM, I can move out in this new direction P, and the CPM kind of grows bigger and bigger. But there's a minimal size CPM that sits in the middle, which has size R. So the 0 section of this bundle is this object here. So I'm going to draw this in the following way. It's not strictly valid. Really, at any point on the space I can move out. You can think of this as moving in the p direction. So this is the O minus n line bundle labeled by. Okay, so now I have some big non-compact space, Calabi-Yau. Phi Leopolis parameter doesn't run. The size of this object that sits in the middle there is fixed. Doesn't change its renormalization group. But it's not quite what I want. What I want is some interesting compact Calabi-Yau manifold. So now we come to step 3. Well, there's tag football after the last lecture, by the way. I was wondering why you would want to tag somebody in football, but then I remembered that you guys have a different game. Okay. So step 3 is to try and get down from this non-compact Calabi-Yau to a compact Calabi-Yau. And this is introducer potential. And we want to preserve supersymmetry. N equals 2, 2 supersymmetry in 2 dimensions is the same as n equals 1 in 4 dimensions. So you know what kind of potentials are allowed there. They're superpotentials. Okay, so we want a superpotential, but this superpotential has a couple of restrictions on it. In particular, it has to be holomorphic in the chiral superfields. It also has to be gauge invariant. And because we want various motor properties, we're going to restrict ourselves to positive powers of p and phi. We're not going to allow powers of 1 over phi. So the superpotential we're going to write is the following. We're going to have it linear in p. So this has charge minus n. And then we write down some polynomial of the phi i's. But this polynomial has to have charge plus n to cancel the charge of this, so the whole thing is gauge invariant. So a homogeneous, okay, this is an approximate spelling, homogeneous polynomial of degree n. Okay, so this means it's a polynomial where every single term in the polynomial has n phi's appearing in it. There may be phi 1 to the n, or phi 1 to the n minus 1, phi 2. Okay, so I've got a whole different bunch of terms I can put in this. Okay, what happens once I've got this superpotential? Well, I still have the d terms here. They don't change, so I still have to impose this. And now I get an extra term in potential. So the extra term, so there's the d terms, which are on the other board, plus. Well, remember, I take the superpotential, I differentiate with respect to each field, and then I take the mod square. So differentiating with respect to p, I get mod g squared. And differentiating with respect to the phi I get this. You guys okay? Did I mess up a little bit? You good? Okay, so I want to still look at the vacuum moduli space. That's the space v equals 0. Imposing the d terms, I have this manifold, this non-compact Calabi-Yau that I've drawn here. So now what new do I have? Well, suppose I have the following condition on G. So suppose that the requirement that dg by d phi is equal to 0 for all I implies that all the phi are equal to 0 for all j. Okay, you know that has to be a solution precisely because this is a homogeneous polynomial. It doesn't have any constant terms, so that has to be a solution. But we're going to suppose that G satisfies this condition. This is called the transversality condition. Okay, what's the meaning of this? Well, because r is greater than 0, you can't cancel it just by turning on p by its own minus sign. So you've got to cancel it by turning on the phi's. So at least one of the phi's has to be non-zero. But if one of the phi's is non-zero, by this it means that one of the dg by d phi's is also non-zero, which means that we have to set p equals to 0. Okay? So having this condition here on G means that the superpotential restricts us to p equals 0. What's more, the first term here sets some polynomial of phi's to 0. Okay, so what have I done? The D terms give me this manifold here, which is this non-compact Calabi-Yau line bundle over Cpn minus 1. Turning on the superpotential does two things. It sets me to p equals 0, but p equals 0 puts me right back to Calabi-Yau plus 1. The second thing it does is it, within the Cpn minus 1. The second thing that it does is it sets this polynomial of the phi's equal to 0 within the Cpn minus 1. So there's some locus here within the Cpn minus 1, excuse me, which is the locus g of phi I is equal to 0. Okay, so what do we have? We have a situation where the phi Heliopolis parameter isn't running because we've introduced the matter fields in just the right way to cancel the one-loop beta function. Because of supersymmetry, there's no further corrections. There's no two-loop corrections. We introduced this p field, which gave us a non-compact Calabi-Yau manifold, but then it also allowed us to introduce a superpotential, which immediately sets p equals to 0 and puts us back on the Cpn we started with, together with an extra constraint, which is this g phi I equals 0. So the vacuum manifold of this theory, that is the space of solutions to v equals 0, is some compact manifold X inside Cpn minus 1, defined by this polynomial g of phi I equals 0. Now, it's a mathematical fact long known to mathematicians that if you take a degree k homogeneous polynomial inside Cpn minus 1, that defines a Calabi-Yau manifold only if the degree k is equal to n, which is exactly what we have here. This is a degree n polynomial inside Cpn minus 1. So this does define a Calabi-Yau manifold. Okay. And notice the way everything ties together. If I tried to define a different degree polynomial here, I would have had to have a different charge here, but then that wouldn't have cancelled my beta function for the phi Heliopolis parameter, so I knew my theory wasn't conformal. So there's this beautiful interplay between what you know in terms of gauge theories about how you make things not run under RG flow, and what mathematicians know in terms of algebraic geometry about restricting yourself to particular polynomials equal 0 inside surfaces. Okay? The extra bit of information you need to know is that the conformal fixed point for a sigma model is the Ritchie-Flat equations Rij equals 0, which are obeyed for compact manifold for the Calabi-Yau. But there's another little extra bit that works out nicely, which is in terms of the anomalies. The typical n equals 2 theories have two U1R symmetries. They're usually called U1R and U1A. U1R is always non-anomalous, but U1A is typically anomalous. And the anomaly is proportional to the sum of the charges of the charged matter. So it's only when the sum of the charges cancel that the U1A is non-anomalous. But in order to have a conformal field theory, you need the U1A to be non-anomalous because it sits there inside the superconformal alpha. So there's all these nice interplays of things going on. I'll tell you what we haven't got, though. What we haven't got is the Ritchie-Flat metric on the Calabi-Yau. Okay, so it's not like we've just
we've got a conformal field theory and nothing's going to change under our G flow. R doesn't change, but you see this space here, G equals 0, this has inherited a metric from the round metric that lives on the CPN minus 1. This isn't the Yau metric. This isn't the unique Ritchie-Flat metric on a manifold with vanishing first choke. And we know it can't be because these metrics are very hard to get. People are spending a lot of effort trying to compute them numerically. You couldn't do it in such a simple way. So what the gauge theory does for you is restrict you to a manifold X, which is topologically Calabi-Yau, meaning it has first Chown class 0. But all the rest is done for you by RG flow. You don't even care what this Ritchie-Flat metric is. You know that under RG flow you've got to end up in an interacting conformal field theory. You know that interacting conformal field theory has to have the Ritchie-Flat metric, at least up to 3 loops. Some strange corrections kick in. Okay, so this is a beautiful way not even to worry about the unique Yau metric that lives on this Calabi-Yau manifold. We're going to do all the computations in the ultraviolet. We know we're going to hit this Ritchie-Flat metric in the infrared, but we really don't care what it is. Okay, are there any questions about my 3 steps to getting a Calabi-Yau from a gauge theory? Yeah. Absolutely not. In fact, well, I could do things like p squared and then a 2n degree polynomial. They're just not going to lead me to a Calabi-Yau manifold. Okay, and the fact that it's linear in P is what's restricting me to something that imposes something on the 5s. If it was quadratic in P, I'd have a P here and I could just solve it by setting P equals to 0. Absolutely not. Yeah. So there's an SUN flavor symmetry which will be broken typically by any polynomial. In fact, I'll mention a few more points on this. Are there any other questions? Okay, so what we've done is we've got a gauge theory whose vacuum moduli space of the solutions V equals 0 is equal to the Calabi-Yau manifold of our choice. It's not really our choice, it's a rather specific one that's embedded inside CPN, but by doing more general construction, we can get more general Calabi-Yaus. So let me now just change perspective a little bit and ask not about the Calabi-Yau itself, but about the moduli space of Calabi-Yaus. Okay, so moduli space of Calabi-Yaus, and actually it's not really the space of Calabi-Yaus, it's more the space of conformal field theories, within the class of which is a sigma model that's got a target space. Okay, so as you know, I'm sure, from Shamit's lectures and probably many others, Calabi-Yaus aren't unique objects. There's ways you can squeeze them and twist them to keep their Calabi-Yau property. And of course, for phenomenological reasons, these cause a lot of headaches and you have to go to huge lengths to fix these moduli. So how do we see the moduli in this perspective? Well, the moduli are the parameters of the field theory we start with. So we put in different parameters into the gauge theory. They give us different Calabi-Yaus coming out at the end of the day. So where are these parameters? Well, there's 2 different classes. One is in this polynomial here that I didn't specify. This is a degree n polynomial in the 5s, but there's coefficients in front of that, each of which is a complex number. Those coefficients determine the shape of the Calabi-Yau. It's fairly clear, right? They determine the curve G inside CPN. The shape of the Calabi-Yaus. So the complex structure moduli these are the coefficients inside this potential G of phi. The other type of moduli you have is essentially the size of the Calabi-Yau, how you can deform 2 cycles. This particular Calabi-Yaus, built in the way I've described, where you start this with a U1 theory, these have just 1 Kähler modulus. So actually, you know that these are related to H21 and these are related to H11. So all the Calabi-Yaus you build in this specific way have H11 equals 1. And the Kähler modulus is the size of the Calabi-Yau, which you can see very easily was the size of the CPN you started. So that was the Filiopolis parameter.
Okay, now yes. Oh, that's right, but that's because that's because it's hyperkähler and you don't really have complex structure. The Kähler moduli are all mixed into one. So you have to treat that as a special case. You also have to treat Riemann surfaces inside P2 as a special case. I'm sorry, I didn't. Yeah, no, it's true. Okay, now there's a crucial fact in string theory that mathematicians realized, I think, about the same time as physicists, which is that the Kähler class R, which is just the size of this guy, actually gets complexified. So there's a complex Kähler class, which is T, and it's equal to R, but the complex bit you add has a very natural interpretation, both in terms of string theory and in terms of this 2D gauge theory. In terms of the 2D gauge theory, this is a theta angle, meaning that it multiplies the term in the gauge theory, which is theta f01. Okay. In terms of string theory, this is the integral through a 2 cycle of B2. Okay, so these are the two different types of moduli that you have. And the one I'm going to focus on here is the Kähler modulus. Okay, so look at the Kähler moduli space. Okay, so what is this? The Kähler moduli space is the space of parameters of the gauge linear sigmoidal that we started with. Okay, it's the same sort of concept we had in the various phase lecture. So it's the space of all possible R and all possible theta. Now I'm going to draw this as a cylinder because R goes from minus infinity to plus infinity and theta goes from 0 to 2 pi. I think I'm the only one in the world who draws this as a cylinder because there's a natural Zamorodnikov metric on this and it looks all essentially. But naively, it's a cylinder, so I'm happy to stick with this. So this is the space of parameters. This is R goes to plus infinity, theta goes around here, and this is R goes to minus infinity. Okay. This is the space of T equals R plus I theta. Okay, so what are we looking at here? This is the parameter space. That means that every single point on this cylinder corresponds to a different gauge theory, because I have a different parameter R or a different parameter theta, and therefore a different conformal field theory in the infrared, corresponding to a different Calabi-Yau, at the very least just changing the size of the Calabi-Yau. This is the moduli space of Calabi-Yau manifolds. Okay, so what we want to ask is what the conformal field theory looks like as we move around in this moduli space. So where have we figured it out so far? Well, so far we've really only looked at it when it has a nice geometric interpretation, which means that everything is very big. Okay, this is like the alpha prime expansion in string theory. So when R is very big, we've understood that this is a Calabi-Yau X contained in CPn minus 1. Okay? But the question we want to answer is what happens as we start to vary R? In particular, what happens when R gets close to 0, or even when R goes negative? These are all conformal field theories that are continuously connected to the Calabi-Yau conformal field theory, and in particular will share some of their properties. But we've got to figure out what's going on here. So this was the main purpose of, well, at least it was one of the main purposes of the Witten's phases paper, was to answer this question. So let me just tell you the answer and then move on to some newer topics. So the D term, remember, looked like the following. And then the superpotential was, well, the superpotential was P G of phi I. Okay? And what we did is we showed that when R is much greater than 0, this restricts us to this Calabi-Yau. So that's
That's this point in modulus. So let's start dialing r, and let's go to the point where r is much less than 0, where r goes towards minus infinity. Well, now the minus signs work differently. When r is minus infinity, to cancel this and make the d term vanish, you've got to turn on p. Okay, phi is not going to help you at all because it has the row minus sign. Okay, so when r tends towards minus infinity, you've got to give a bev to p to cancel it. Okay. But giving a bev to p breaks the U1 gauge group, but it doesn't quite break it completely. It breaks it to Zn because p had a charge n under the U1. What does that do? Well, it's managed to sort this guy out. But we're left with a bunch of phi's. Replace p by its expectation value. What we're left with is a bunch of chiral multiplets phi I. We don't have to worry about the gauge transformation anymore. That's been broken. So they're chargeless chiral multiplets, but interacting through this particular superpotential. Okay, so just a bunch of scalar fields with a superpotential. This is a well-known kind of model. It's just called a Landau-Ginzburg model. So this is a Landau-Ginzburg model. And we actually met something very similar yesterday. Remember yesterday I looked at the theory that was just, well, I called it sigma, but I could just as well call it phi to the n for superpotential. That's a Landau-Ginzburg model that's equal to a minimum. So this is a conformal field theory. It's simply scalar fields floating around with a particular potential, close to a conformal field theory. In fact, you've still got to worry about this Zn object, this Zn gauge rotation. So in fact, it's a Landau-Ginzburg orbifold. You have to divide out by that Zn. It's a small sum. Okay, so over here we have Calabi-Yau manifolds. Over here, continuously connected to it, we have something that looks very different. We have a Landau-Ginzburg, well, really a Landau-Ginzburg orbifold. And again, there's certain things you can compute in the Landau-Ginzburg orbifold that will match exactly what you would compute in the Calabi-Yau. Things that are dependent on pendulum. So again, this was an old story from the 1980s. It's often called, the point r goes to minus infinity is often called the Gepler point. It's a point where the theory that you're interested in is actually very, very simple. It's just a bunch of scalar fields with some orbifold and maybe some potential. So I think one of the driving motivations for Wickett's paper was to understand things that have been loosely figured out in the literature that Landau-Ginzburg models have something to do with Calabi-Yau models. But this is how you see it. You write down the gauge theory, you dial the Phi-Heliopolis parameter, you go smoothly from one to the other. There's one other point in this moduli space which is going to be important, and that sits somewhere in the middle here. Somewhere in the middle of this moduli space, that's for a specific value of both r and theta, there's a point where all correlation functions in your conformal field theory diverge. Okay? They all go to infinity. It's a very sick point. It wasn't at all clear in the early to mid-90s what to make of conformal field theories close to this point. Okay? What you can see from the gauge linear sigma model is you can figure out where this point is, but you can't figure out what to do with it. So how this point comes about in the gauge linear sigma model, if you remember, this was the d term. But then we have this Coulomb branch field. This is a vector multiplet scalar that really we haven't been worrying about at all. Okay, so I said we didn't have to worry about this because when r was non-zero, you had to turn on either phi or p, and that means that these turn on and that means that this can't. However, when r goes to 0, notice that there's a new possibility. There's a Coulomb branch that emerges that has nothing to do with your Calabi-Yau. Suddenly you can set phi and p equal to 0 if r is 0, but sigma can take any value you like. So it's the emergence of this Coulomb branch in the gauge theory which signifies the breakdown of the conformal field theory at this point. Now, this point isn't necessarily at r equals 0. It gets finite quantum corrections in the full quantum theory, but nonetheless it persists. And so using the gauge linear signal model, you can figure out where this point is in moduli space. To figure out what it means requires going beyond the conformal field theory or any signal model. From the string theory perspective, Strominger showed how this point was coming about because D branes, which are wrapped around 2 cycles, become very light at this point and then become massless. And in fact, with Green and Morrison, they showed something quite beautiful. There's actually the complex structure moduli space of another Calabi-Yau, completely different Calabi-Yau manifold Y, which attaches to this point. And what happens is as you approach this point, the D branes in string theory become massless and massless. At this point, they can condense just like Cooper pairs in a superconductor, and you get a topology changing transition where at 2-cycle strings, a 3-cycle grows, you find yourself in a completely different Calabi-Yau manifold. Okay, so this is a really nice story, but not one I'm going to go into in this lecture. Okay, so that's my summary of work in the 1990s of trying to understand Calabi-Yau manifolds from gauge theory. So are there any questions before I tell you about some new stuff? No? Okay, so let me tell you about some new stuff. So there's a bunch of ways you can generalize this. You could, for example, write down theories with lots of U1 fields, lots of chiral multiplets with different charges between them, something like quiver theories. You get a whole bunch of different Calabi-Yaus. All those Calabi-Yaus are what are called complete intersections inside toric varieties. The toric variety is related to the fact that you start with U1 fields. The complete intersection is related to the fact that you write down a superpotential and just look at the zeros of this potential. Okay, so what I'm going to tell you is how you can, using gauge theories, look at Calabi-Yaus which are not in toric varieties and are not complete intersections. Okay, so it's a new way of constructing Calabi-Yaus using gauge theories. In particular, these Calabi-Yaus are interesting because the mirror symmetry of them is really much less understood than for the case of toric varieties. So let's go back to the beginning. By the way, at this point, some of the slides that I gave you start to be more relevant. It starts about halfway through. Okay, and what we're going to do is a kind of trivial generalization. In fact, this was even in Witten's phases paper, except nobody really made use of it in the 15 years, maybe 10 years after that. So what we do is, instead of having a U1 theory, we have a UK theory. And we take n chiral multiplets in the fundamental representation. What does the D term look like? Well, it looks like the following, and now we should divide out by UK gauge transformations. So unitary representations. Okay, so this is going to be the analog of the CPN that we got to begin with. The question is, what is this space defined by this algebraic constraint equals 0, so there's a square up there. This is a matrix constraint, notice that's the A and B indices, and dividing out by these UK gauge actions. So this is the way you should think about this. The phi's have 2 indices. One goes from 1 to k, which is the gauge index, and one goes from 1 to n, which is the flavor index. So think of these as k vectors in Cn. Okay? And we're summing over the I, so this is an inner product in the Cn. So what this relationship here is asking is that you look for k vectors, labeled by 1 to k, that are orthogonal, in fact, orthonormal up to this factor I. Okay? So setting v equals to 0 gives you k orthogonal vectors in Cn. So the space of all solutions to v equals 0 is the space of all possible orthogonal the normal k vectors. However, then we have to divide out by UK transformations. So what does that do? If I've picked a particular basis in Cn, the UK transformations just rotate that basis, but they don't change the k-plane that that basis defined. Okay? So the space of all solutions of p equals 0 modulo UK gauge transformations is the space of all k-planes inside CPN. So this is the space of k-planes in Cn, and there's a name for this. This is called the Grassmann. So we're going to label it GKN. So GKN is the Higgs branch of a UK gauge theory with n fundamental objects. That's the Grassmann. Nothing to do with anti-commuting. Same guy, I think. Okay, good. So step 2. Well, we have exactly the same problem as before. The Grassmannian is, and the Grassmannian is kind of like a non-abelian generalization of CPN, essentially. G1 comma n is exactly CPN minus n. So it's not conformal. The Filiopolis parameter R here runs at one loop. The Grassmannian shrinks to 0 size. We've got to cancel that. We're going to add more matter fields. Okay, so step 2 is add more matter fields. To cancel the beta function that this theory would have for the Filiopolis. Okay, so what matter fields are we going to add? Well, as before, there's a bunch of possibilities. One thing we could do is add n chiral multiplets in the anti-fundamental representation. That would cancel these guys in the fundamental representation, would lead to something very dumb. So here's the clever trick. What you do is you add chiral multiplets that are charged only under the U1 of the SUK. So, sorry, the U1 of the UK, not under the SUK. So we're going to add matter fields. So we add S chiral multiplets. So S is just a number. And I'm going to call them P alpha. So alpha goes from 1 to S. With charge minus Q alpha under the U1 that's the central part of the UK. If you want to be fancy about this, you can say they're in the det to the minus Q alpha representation of the UK. But it just means they're charged under this central U1. Okay, now in order to cancel the anomaly that you get from these, to cancel the anomaly or to cancel the running of the Filiopolis parameter that you get from these n here, the condition is, so if you want the Filiopolis parameter not to run, the condition is that the sum of these charges you give these guys has to equal n. Yeah. It really is only the U1, that's right. Yeah. In fact, you kind of know that these Filiopolis parameters are only there if you have U1 parts of the theory. If you just have SUK, you can't. That's a good way to think of it. Okay, so what have I got if I do this? Well, you know, by this stage before I had some manifold which was CPN, but now it's a Grassmannian, and now there's a bunch of non-compact directions, which are these directions P that sit over it, and the whole thing is sum of line bundles O to the minus Q alpha fibered over this Grassmannian. Okay, so it's a Calabi-Yau precisely if the sum of these Q's is equal to n, but as before, it's non-compact. It's not really what we're interested in. I have to quarter past. Okay, so now remember step 3. And that's introduce a superpotential. Okay, so remember what we did before. We took these P's, which were charged under the U1, and we multiplied them by these Phi's, which were charged under the U1, to get a gauge invariant superpotential. Here we're going to have to work a little bit harder, because these guys transform under the full UK, whereas these guys only transform under the U1. So somehow we need to patch all this together to make everything invariant under the full UK. So this is the way you do it. You introduce baryons Okay, so you introduce a bunch of baryon variables by taking the antisymmetric product of a bunch of the Phi's, okay? So these are baryons that are now guaranteed to be invariant under the SUK part of the UK, but they're still charged under the U1 part. The U1 part is essentially baryon number, so you know these have a charge plus or minus. Interesting comment, I didn't know about this. Mathematicians discovered baryons in the late 1800s. They call them Plucker coordinates, or maybe it's Plucker coordinates. I don't know, there's an umlaut somewhere in there. But they have precisely baryons for Grassmannians. Okay, so these are invariant under SUK. But not under the U1 part, but that's perfect for us because we've already got something which is charged under the U1 part, which are the P's. So now we can introduce a superpotential where for each P that we have, we can write down a polynomial, but now a polynomial in the B. Okay. So this is a homogeneous polynomial degree Q alpha, whose coordinates are the baryons, which are already SUK invariant. Okay, so the baryons are SUK invariant, so the whole thing is SUK invariant. And the fact that this has degree Q alpha and this has charge minus Q alpha guarantees the whole thing is U1 invariant. Okay, so what do we have? We have this Grassmannian. We have line bundles. We impose this superpotential. It does exactly the same thing it did before. Firstly, given particular transversality conditions, I'll come back to that. It sets P equals to 0, and then it also sets these G's equal to 0. So just as we had before, we're no longer allowed to move this way because of the superpotential, and what's more, you can't go any way you like. In this, you're restricted to some Calabi-Yau hypersurface defined by G alpha is equal to 0. Now there's S constraints, where S was the number of Okay, once again, this is guaranteed to be Calabi-Yau. So this gives us an X inside the Grassmannian. That's Calabi-Yau. Okay, oh, I was going to say one thing. This strange constraint I had on the G's, that when you differentiate them, set them equal to 0, the only solution is that all the coordinates are 0. That transversality constraint translates into the fact that the hypersurface you put here is smooth. Essentially, it means the tangent vectors are well defined everything. So it has something nice and geometrical, both in this case and the Taurus. Okay, so as I said, this is a completely trivial generalization of what we originally did for CPN. It was in Witten's first paper. But to do the rest of the analysis, remember I had the cylinder, that's the moduli space of the Calabi-Yau. when I dial r from being plus infinity down to 0, what's happening? Well, this non-abelian gauge group is becoming unhiggsed. And if you want to understand the quantum dynamics of what happens to the Calabi-Yau conformal field theory in this regime, you've got to understand the quantum dynamics of a non-abelian gauge theory in 2 dimensions. And remarkably, there had been almost zero work on this until last year. I mean, really zero. The very basic properties of these theories, like Witten index, vacuum structure, when they flow to conformal theories, what happens when you dial parameters, nobody had known any of this. Okay, so this was, I think, the reason why people didn't look at these parameters. So what I'd like to do now is tell you what Kentaro Hori and I did last year, and explain some results about non-abelian gauge theories and how you can use it to prove a mathematical conjecture about these Calabi-Yau manifolds that live inside G here. A mathematical conjecture which I don't think mathematicians believed until we proved it. So it's quite nice. Okay, are there any questions? 20 minutes, should be okay. Okay, let me firstly tell you something a little surprising. If you want to build Calabi-Yau manifolds, you don't have to restrict to Calabi-Yau threefold, because after all, they're the ones we're interested in. If you want to build Calabi-Yau threefolds inside CPA, and the ones I wrote, you'd have to build them inside CP4, I guess, to get a threefold. But in fact, you can easily generalize it to include more potentials, which are strictly greater potential. So if you want to build Calabi-Yau threefolds inside projective spaces, there's many, many hundreds of thousands of ways you can get different ones. It's extremely easy just to generalize and generalize and generalize. If you want to build Calabi-Yau threefolds that live inside Grassmannians like this, there's an extremely finite number of ways to do it. Where extremely finite in this case means 6. Okay? So what happens here is that when you start to increase the gauge group or the number of matter contents, the dimension of the Grassmannian grows much quicker than the number of constraints you can try and put on to keep yourself down to 3 dimensions. So it's a simple exercise to do, but you find there's 6 ways to put a Calabi-Yau inside a Grassmannian that isn't complex projective space. Okay. So 6 is kind of a nice number because, I'm not saying these 6 are particularly important for phenomenology or for any reasons, but if you're into these kind of things, you can sit down, you can get to know each one kind of personally, understand what's going on with it. There are conjectures by mathematicians recently about what the mirrors are, so you can play lots of games, summing instantons, doing anything that turns you on, essentially. However, of these 6, there's one that is really very special, and that's the one I'm going to tell you about. So, a special Calabi-Yau is a U2 gauge group with 7 chiral multiplets. Okay, it's not at all clear immediately what's special about that, but when you start playing with it, it turns out that the fact it's 2 and 7 is kind of important. So, let me tell you about this special Calabi-Yau and this conjecture of a graduate student in 1998. I googled this guy. He left mathematics and is now working, I think, for bioinformatics. Yeah. No, this is just a classical statement about the Higgs boson. It's not a deep statement. If I was to build more gauge groups, more matter contents, quivers, I could probably get. Oh yeah, so this is, in each case I'd have some modulo space, and here, as r goes to infinity, I'd have some Calabi-Yau, and understanding what the dynamics is here, for those 6, we know the answer for 1 because it turns out you can rewrite it in projective space, and this one I'm going to give. So there's 4 of those 6 where we actually don't know what's going on here. But at large radius, it's all classical. Yeah. Okay, so what did Rodland say? Rodland said the following. The Calabi-Yau of interest is X inside G27. So remember what these things mean. This is a U2 gauge group. This is 7 fundamental chirals. And we need to know the the charges of the guys we gave to cancel the beta function, those things I call Q alpha. And Q alpha in this case is equal to 1, 1, 1, 1, 1, 1. Okay, so you have 7 objects, each with charge -1 under the U1 central charge, central U1 of the U2. Okay, this is Rodland's conjecture. Here's the moduli space, and so I should have drawn that under what I just wrote. Here's the moduli space. This is R goes to infinity, and this is where we know that this particular Calabi-Yau is constructed using the gauge theory limits. Rodland's conjecture was that here there's another Calabi-Yau called Y. Let me tell you what Y is. Y is the Pfaffian Calabi-Yau. This is defined in the most ridiculous way you could possibly imagine, and how people come up with these things I don't know. You do the following. You take the space of all 7 by 7 antisymmetric matrices. Space 7 by 7 antisymmetric matrices. The number of dimensions of this space is 7 times 6 divided by 2 to 21. So it's a 21-dimensional space. Every point in this space is a 7 by 7 antisymmetric. However, it turns out you're not interested in all the matrices. If you can take one matrix and multiply it by an overall scale factor, complex scale factor, you'll consider that equivalent to the matrix you get. Okay? So you want to divide out by overall scaling. I should say these things are all complex. Okay, so 7 by 7 antisymmetric matrices, but you don't care about overall scalings. So that gives you a space which is CP20. Okay, so here's CP20, and every point in CP20 is defines a 7 by 7 antisymmetric matrix after this overall scale. Now, your typical antisymmetric 7 by 7 matrix has rank 6. Okay? It's not rank 7 because it's antisymmetric, so it's rank 6. As you move around in this CP20, occasionally you'll hit a special antisymmetric 7 by 7 matrix whose rank is less than 6. It has to be 4 because it's antisymmetric. So within CP20, there's some locus, like this, which is where the 7 by 7 antisymmetric matrix is degenerated to become rank 4. Good. Now what you do is the following. Now you take a CP6, and you get this CP6 and you embed it somewhere in this CP20. Where is your choice? The way that CP6 intersects with this locus of rank 4 antisymmetric 7 by 7 matrices defines a Calabi-Yau 3. Okay? And that's the Pfaffian Calabi-Yau Y. Who knew? Okay, so let me just define Y. Let A be an antisymmetric 7 by 7 matrix. Consider the locus such that the rank of A is less than 6. And Y is the intersection of this locus with CP6. Okay, good. So there's this completely ridiculous Calabi-Yau manifold called Y. And what Rodland conjectured was that X and Y lived on this big moduli space. And if you were to dial the size of X smaller and smaller and smaller, at some point you have to stop thinking geometrically, you have to think in terms of CFTs. If you keep going to negative R, you're going to get to this Pfaffian Calabi-Yau. Okay, well, what was his evidence? Well, he computed Hodge numbers of these two things, they agreed. He kind of had some idea about what the mirrors were, and thought that they also looked the same. He this was Rodland's conjecture. I should say that this isn't, at first glance, completely ridiculous. Remember, before we dialed R, went negative, and didn't find another geometrical space. We found some Landau-Ginzburg theory, which defined a conformal field theory. However, there are examples where you dial R, it goes negative, and what you get is another geometric Calabi-Yau. Those examples are called flop transitions. Okay, so this is very reminiscent of what's called a flop transition in Calabi-Yauology. However, this isn't a flop. Okay, so this is a little bit technical, but if you have a flop transition, typically where you go from one Calabi-Yau to another, the two Calabi-Yaus have to be birationally equivalent. That essentially means there's a one-to-one complex map between them. And it turns out that this Calabi-Yau here, y, is not birationally equivalent to x. And in fact, there was some kind of folk theory in mathematics that if two Calabi-Yaus given the same modulo space, they should be birationally equivalent, which is why this is a surprise. It's a little bit technical, but nonetheless, it's a bit of a surprise that this could possibly be true. So, okay, so when Kintaro and I were writing this paper to prove this, we were actually going to call this a flop. But Dave Morrison, who was on the naming committee for the flop, it's astonishing such things exist, told us that because this was not birationally equivalent, and the definition of a flop is that these things are birationally equivalent, we couldn't possibly call this a flop. So we decided to call it a glop, which is a name which is uniformly not caught on in the mathematical community. Okay, so let me show you how this glop transition can work. 5 minutes, okay. Might take 7 minutes. Okay, so the proof. So what have we got? We've got a U2 gauge theory plus 7 chirals in the fundamental representation plus 7 chirals with charge -1 just under that U1 part of the U2. The D term okay, this is the constraint from the D term. The F term that I write down, well, it's some superpotential. I'm going to put a mu in here. Okay, mu is a mass term, but really I want to take mu goes to infinity, because that's going to really restrict me to the Calabi-Yau manifold X that I want to. These are the coefficients of that polynomial. Okay. If you want to get ahead of the game, notice I'm calling these A, and I called my antisymmetric matrix as well. And these are the barriers. Okay, so this is the gauge theory which I would write down to define what's on the very right-hand side of this modular space. Now, somehow, if Rodland's conjecture is correct, this same U2 gauge theory should know all of this rubbish about antisymmetric matrices degenerating to rank 4, blah, blah, blah. Let me show you how that works. And it's rather cute, because you have to understand quite a lot about the dynamics of non-abelian gauge theories. Okay, so let's set R much less than 0, which is where we want to be. When R is much less than 0, you don't cancel it by the phi's, you cancel it by the p's, because the minus signs work out. So this means that pi is not equal to 0, which, in fact, let me set the pi squared is equal to R, mod the U1 gauge action, which sends the pi's to e to the minus I alpha pi. So what does this define? Well, this is something we've seen over and over again. This defines complex projective space. There's 7 of these guys. So over at left infinity of the modulo space, we have a CP6. Okay, that's nice. There was some CP6 standing in this Pfaffian definition. Okay, so here's CP6. But now comes the tricky part, because we haven't dealt with the SU2 part of this gauge group, and an SU2 gauge dynamics is going to be very strongly coupled. So at every point on this CP6 is an SU2 gauge theory with 7 fundamental chiral multiplets. Okay, the U1 part's been Higgsed by the P's, So we have a CP6, and at every point on this, there's an SU2 gauge. Now, the superpotential for this is the following. So now, changing the P changes where you sit on the CP6. Okay? So as you move around on the CP6, the superpotential, which is giving a mass term for the chirals, is changing. So this is a mass term. For these fundamental chiral multiplets. And what mass you have changes as you move around on the CP6. Okay? Every point here, SU2 gauge theory, 7 fundamental chirals whose mass is changing. Okay, so what we need to do, if we're going to make any progress with this, is understand something that should be fairly simple. It's to understand that SU2 gauge theory with 7 chiral multiplets. Well, what happens with this theory? What's the vacuum structure of this theory? Does it break supersymmetry? Is it supersymmetric? Does it have normalizable ground states? And all the very, very basic things that you could want to ask about this theory, but remarkably have never been proven in the literature. So in particular, how many supersymmetric ground states does this have? Or what's the Witten index? You know, Witten defined his index in 1981, and nobody had computed the Witten index for 2,2 theories, SUK plus N fundamental. Okay, it's kind of amazing. For UK, it's trivial. It's K2Z. But for SUK, it's much less trivial. So let me tell you the Witten index for SUK plus N chirals. Okay, I'm not going to prove it to you because of obvious time constraints, so I'll just tell you the answer. The answer is actually really peculiar. The answer I have to give you in terms of a combinatoric problem, which then you have to sit down and solve. If you're feeling lazy, for K up to about 12, for N up to about 20 or something, we put a huge table at the beginning of our paper and figured it all out. It becomes a drag when these things get large. Okay, so you do the following. You find the nth root of unity. Okay. So n is the number of chiral multiplets. Draw a wheel and put n spokes on the wheel. Okay. And on each spoke, put the appropriate root of unity. Okay. So I've got n spokes, n is the number of chiral multiplets. To figure out the Witten index, you have to do the following. You have to pick k spokes. You pick this one, you pick this one, and you pick this one. But you have 2 requirements on picking the spokes. So you pick k spokes, but you've got to guarantee, so let's that essentially means picking k integers from 0 through to n minus 1. You've got to guarantee that when you sum up all those roots of unity corresponding to these spokes, you don't get 0. Okay? For example, with 3 I'm okay. If I was to pick 2, I couldn't pick this one and this one because they would sum up to 0. So you've got to do that. Then, however, you've got to insist that if you can pick some configuration and spin the wheel, then that's only counted once, meaning that this configuration is the same as a configuration where everything is just rotated. Okay? So modulo rotations of the wheel. Okay, that's the counting problem you have to do. When you figure out the answer to that, that tells you the number of supersymmetric ground states to SUK plus N. It's kind of weird. I can show you the proof. I put some proof in the slides, but there's a few loopholes. Okay, good. How does this help us? Let me just run through a few examples. If n is less than or equal to k, this theory dynamically breaks supersymmetry. And probably it doesn't have a normalizable ground state. If n is equal to k plus 1, there's a unique ground state of this theory. Okay. What does this have to do with Rodman's conjecture? Okay, let's go back to our problem. SU2 plus 7 chirals. Well, you can draw the wheel, you can play the game, you can choose all your spokes. You find there's 3 vacuum. However, we don't really have SU2 with 7 chirals because we have a mass term. And the mass term includes this bit mu, which strictly speaking is kind of artificial. Mu should be going to infinity. So in fact, this superpotential, which is changing as you move around CP6, is making some subset of these 7 chiral multiples infinitely massive. So the question you want to ask is not really what's the Witten index of SU2 with 7, but it's what's the Witten index of SU2 with the number of chiral multiplets that are left massless when you include this superpotential. Okay. So we define AP ij is equal to aijk pk is a 7 by 7 antisymmetric matrix. That's nice. When the rank of A is equal to 6, which is a typical place somewhere on here, well, when the rank of A is equal to 6, 6 of these fundamental chiral multiplets get massive, and you're left only with 1. Because what you're left with is SU2 plus 1 light chiral. But with an index calculation, that doesn't have any supersymmetric ground state. When A degenerates and its rank goes to 4, what you're left with is SU2 plus 3 light chirals. And that theory has precisely one unique ground state. So what's going on here is the following. As you move around this CP6, which was sitting at the far left of the moduli space, the masses of the chirals are changing. And for nearly all values here within this CP6, the masses are so big that the theory doesn't have any ground state. However, on some particular locus, which is where the rank of this matrix is equal to 4, the Witten index tells us that there's precisely a unique vacuum, and this is where the theory could possibly live. So what's happening here is the strong coupling non-abelian dynamics are picking out precisely this strange Bathian Calabi-Yau out of the gauge theory. So this is a very new way to get Calabi-Yaus out of gauge theories. It involves using the non-abelian gauge dynamics in a crucial way. We now have 2 examples. We have this and we have a Calabi-Yau 5-fold. But I suspect that there's a lot more that can be dug out of this sort of way of constructing Calabi-Yaus. Okay, I'll finish there. Thank you for your attention.